boa tarde a todos. Vou falar algumas palavras em português, depois a gente muda para inglês para a palestra. Então, a gente está dando início a mais um ciclo de seminários de apresentação, que são seminários em que os novos pesquisadores do IMPA fazem uma apresentação geral sobre suas áreas de pesquisa, seus trabalhos recentes. E, bom, a gente vai ter duas apresentações hoje, né, do Pavel e do João Pedro. Então, sem mais demoras, so let me introduce our first speaker today. It's Professor Pavel Petrov, and he will tell us about mode parabolic equations, mathematical properties, numerical solution and applications in underwater acoustics.
Hi everyone, very welcome to my introductory lecture. I'm Pavel Petrov, as Enrique kindly introduced me, and today I'm going to talk about one of my research lines, which is I think the most developed, which is related to mode parabolic equations and their applications. I'm going to give the talk in English. I hope everyone is okay with that, because I don't even know how to name some of those things even in Russian. So I'm sorry if it's inconvenient for anyone. So let me start. I'll talk a little bit about my background to introduce myself and to show my motivation to do what I'm doing now. So I graduated from Irkutsk State University, which I guess anyone is not aware where it is, but it's somewhere in the middle of Siberia. My university education was in pure mathematics, and my diploma was in combinatorial group theory. So I'm kind of drifting towards more applied things throughout my career, but still, by my education, I'm rather a mathematician. Then I joined a PhD program at Illichov Oceanological Institute, so that sounds already quite applied, although our department has been doing more of theoretical things, more related to mathematical physics and to simulation of various phenomena in the ocean. And I was attracted by the opportunity to do some research in non-commutative calculus, which actually was not very successful attempt, because it's more like people wanted to do some non-commutative calculus rather than doing non-commutative calculus, but I discovered that later on. And my first ever paper published was some application of non-commutative calculus to the derivation of what is called transparent boundary conditions. So the boundary conditions which allow some waves to propagate through the domains in which you are performing the simulation, so that it does not spoil the solution in the interior of the domain. And the best ever compliment I had was a compliment from a referee who has written that he enjoyed the way we derived some formula. That's the best ever compliment I had. But since that time, I was starting to drift towards more and more applied things. And at some point, I kind of felt very much dissatisfied with the fact that we are doing research only for the sake of research, especially because in Russian institutes, you're not supposed to teach in research institutes. You are only full-time researcher. You can supervise PhD students, but that's more or less it. So you don't give lectures. So kind of at some point you start feeling useless a little bit. And normally at the universities, people do some social impact by sharing their knowledge, sharing their education with students. And if you don't even share, you start feeling kind of uncomfy with that. And that was my feeling. And then, after the defense, I started doing some research at geophysical fluid dynamics, and I found some application for what I've been doing in my PhD. An application was a problem of acoustic noise monitoring. So I wanted to be applied, but whenever you try to do something applied in acoustics, most people end up with doing some military things, which was the opposite of what I wanted to do all the time. So And I discovered this nice area of ecosystem acoustics. Ecosystem acoustics means you do some acoustics to preserve some marine fauna, to preserve some animals, well, more or less to do some good things rather than do some things that will eventually kill someone, yes? So that was very attractive for me, and I kind of, well, found some internal comfort when doing this research, which is like research, but at the same time, it ends up with something which sometimes is used for good things, so to say. Yeah, and then I started building my own research group, and at some point I became head of laboratory. Then I did habilitation, which is equivalent of what's called here livre docencia. And then I was, at the end of my work at POI, I was promoted to principal researcher, which is more or less the highest possible level. And then I moved to IMPA. So here I am. And so somewhere at this point, just after my defense, I started doing the things I'm doing. And yeah, so this kind of was motivated by some activity which was taking place there in Russia, in the far east of Russia. Like there we have a Sea of Okhotsk, where they do a development of oil and gas deposits. And when developing like oil and gas deposits offshore, there comes this issue of protecting marine mammals from the noise, because when you develop some oil and gas, you do a lot of noisy activities. Pile driving, seismic survey, a lot of things. And people who were doing acoustical monitoring, so measuring the noise levels and saying if the levels are not too high to affect in a negative way marine animals, kind of approached me and invited me to join, because I was doing the things which was like solution of wave equation, by using these transparent boundary conditions, which could be used for this purpose, to quantify these noise levels, to quantify these pulses, simulate this propagation, and obtain something additional to the measurement. But I'm going to talk about that a bit later. Yeah, so I was super naive at that time. I thought, wow, what kind of problem is that? It's like wave equation. Yeah, it's easy to solve. It's linear. You can solve it with whatever tool you want. Finite elements, finite differences, whatever. It will work fine. That's going to be fun. No way. Okay, whenever it comes to real scale problems with real size of the domain, real content of the source in terms of frequency band, and so on and so forth, you quickly realize that you are so limited by your computational resources. Nothing fits your computer memory. Nothing fits your, let's say, time limits. And okay, it's theoretically doable. It's theoretically super easy. But practically, it's not possible in any reasonable time with any reasonable resources. So instead of doing this thing of directly solving wave equation, you need to find another way. You need to be smart. You need to simplify the problem, not spilling any physics out of it. So like staying within, let's say, some realistic approximation, you need to solve that. And there came this idea, which was very much supported by ExxonMobil, who was operating at that time in Russia, and who was our, let's say, long-standing partner, to start a project on this mode parabolic equation, which were a promising tool to do this simulation in 3 dimensions, maybe not in real time, but close to real time, in reasonable time, handling these sort of practical problems. Yeah, and we had this project, and we had the first prototype, and it was very promising. So the project was approved, and the research continued, and eventually we developed some tool for this propagation, which was first like MATLAB prototype, but then real C++ industrial grade code, which was still being used at POI whenever they are invited to do some acoustical monitoring. They do measurements. But most of the things they do with simulations, and the simulations are accomplished with this very code. Yeah, so it's, as I said, it's an active use, and it was like very nice benchmark for us. So sometimes the people, like in this international community of people doing computation, simulation, theoretical and computational acoustics, they gather and they do some kind of comparative benchmarking of the models. What can solve what? What is the accuracy? What is the reliability? Whatever. And that was a very big workshop in Cambridge in 2022. And a lot of people have presented their methods, their models, their software, and I was kind of very proud that there was one specific problem which only we were capable of handling. Yeah, so, and it was like very good benchmark for and very good sign that what we are doing is nice. Yeah, and we plan to start a very ambitious program with ExxonMobil, including biologists, mathematicians, physicists, to do this for environmental purposes, and also including fishing, because fish is also affected by the sound. Originally, it was only for marine mammals, but then it was cancelled due to the war. And what is good about that, like we had some projects with Russian oil and gas companies, but when I moved to Brazil, like one of the first things, like my colleagues and my collaborators from Exxon immediately asked me whether we can start a project. And now we are putting together this project at IMPA, and hopefully it will start reasonably soon. Well, and it will be probably co-funded by Exxon and Total Energies, and that will do the things, but with also including directivity pattern of the sources. So that's kind of where this line of research comes from. Yeah, and I want to a little bit introduce this area of marine noise and why it needs to be quantified. Well, I'm probably going to show too many pictures and not so many theorems to your taste. So, but because like I think I'm somewhere at extreme applied part of the IMPA, so maybe it's a bit unusual, but at least like I hope it will be understandable and a bit entertaining. Yeah, so why the noise is so important? Why we talk about soundscapes? Why we talk about the noise pollution of ocean? Why we talk about these things? Well, the answer is because for marine animals, their hearing is same thing as vision for us, because you can't see far away in the water and you have to rely on your hearing, and you have to rely on the sound. You have to rely on acoustics to sense the environment, to navigate, to find your prey if you are a predator or whatever. And look, if you look at this huge and beautiful animal, sperm whale, which is the largest animal on the earth, why it's so large? Because you see large part of its body, large part of its head, just above the skull, here, this part. This is some sort of tissue, some fat tissue, which is called spermacet, and which is basically a huge acoustic transducer, which allows it to navigate, to see the fish, to see like a squid, to find a prey, and yeah, to basically to feed. Yeah, so it's like huge living acoustic transducer, basically. So it needs hearing a lot more than it needs eyes, right? And what does it mean for if its environment is polluted by the noise? It's like some sparkles around your eyes all the time, 24/7. Imagine that. Imagine how disturbing is that. It doesn't necessarily kill the animal, but it disturbs it. It stops feeding. It stops like living normal way. It stops like breathing, stops everything. Yeah, and sometimes it goes aground. And scientists think that one of the reasons to go aground for the whales is because of this noise, because of this noise pollution. But it's not only whales. Also fish is affected by the noise. Also even mollusks, like scallops or whatever, they are also affected by the noise. For example, there is research showing that if you have a scallop, when it hears too much noise, the contraction of its heart, or what is scallop's equivalent of heart, it becomes like 2 times slower. Yeah, so it starts growing, starts like functioning in a normal way. Yeah, so noise is extremely dangerous for marine mammals, and it's kind of everyone is knowing about like oil spills. Everyone is aware of microplastic pollution, everything, but now people start to realize that noise is just as important as those sources of pollution as well for the environment, especially for marine environment. And these levels of noise are growing year to year because there is more and more seismic, there is more and more shipping, and so on and so forth. And it's very, very important that we understand that, we quantify that, and we protect our environment from that. Yeah. So here are some data about what typical noises look like. So this is a typical shipping noise. I'm not sure if frequency scale is very visible. So it's somewhere within few hundreds of hertz. If you look at the typical seismic survey pulses somewhere away from actual spot of the seismic survey, it also like few hundred hertz, like broadband, which means spans throughout several tens of hertz. And, yeah, that was unintentional. And it somehow overlaps with the hearing limits of marine mammals, which are shown here. The blue line is something like hearing limits of big whales, like blue whale or spur whale or something like that. And the red one is somewhat like something for smaller animals, like dolphins, orcas, like that. So there is clear overlap, especially for low frequency mammals. And for the fish and for the mollusks, there is so little knowledge we don't even know how much the noise is disturbing for them. Yeah, and like we are only starting to understand what are the limits, what are the thresholds, how to mitigate that, how to quantify that. Yeah. So I wanted to show that although ocean is big, major part of the noise and major part of activities are localized on the continental shelf, like a very thin area close to the continents, close to the shore, where most of human activity actually takes place. Yeah, so noise is mostly localized there in shallow water, as we say. We call it in acoustics. And typical sources of noise, like oil platforms, wind farms, and shipping. Yeah, and what are the metrics to quantify noise? One of the metrics is known as SEL, sound exposure levels. I'll use this abbreviation a lot throughout my talk, so I want to draw your attention towards it. So it's basically an integral of squared acoustic pressure over the time. So that's how much noise you have in this time frame and this very location. You can do the integration using Parseval's identity. You can do the integration in frequency domain likewise, which is sometimes a lot more practical. And for example, for gray whales, the threshold is, let's say, 156 decibels relative to 1 micropascal squared. That's how much they can take, times second. Yeah? So that's how much they can take. If they get more, they don't die, they don't get hurt directly, but it's known that they stop feeding. And basically, what is a whale? Whale has to feed all the time. It's eating throughout its entire life. And they migrate, and once they stop feeding, sometimes when they get into cold water, they can't survive. So it does not affect them immediately, but it surely affects the entire population with some time delay. That's what I'm going to, what I wanted to explain. Then why do modeling? Why you need mathematics for that? You can do the measurements, right? So these are typical measurement stations, like acoustic buoys, which you can deploy, which you can measure, you can quantify. What's the problem about that? Why you need mathematics? You see, I'm giving some warm hugs to some of acoustic transducers, like on board of some research vessel. Well, yes, look, if you are super rich, you have all the resources in the world, like you are a big oil and gas company. You can maybe deploy few of them, like 10, maybe 20 in some area. Otherwise, it becomes even too expensive even for somebody very rich. So, and how much, if you have hundreds of kilometers of the shore, how much of these measurements you can afford? Not so much, that's the answer, right? And most of the work you have to do using mathematics, using modeling, using simulation. You can rely on these measurements as a reference to validate, to check, to establish the reference levels for the source, but no more than that. Most of the work has to be done by math. You can't quantify marine noise. You can't go beyond hello with quantifying marine noise without mathematics. So without solving PDEs, basically. That's where it goes. Yeah. So now I'm going to show some equations. Yeah. So I'll start with what's the general framework of all this thing. The general framework in which we do this computation is called normal modes. What are normal modes? Basically, if you look at the typical three-dimensional Helmholtz equation with a 3D elliptic equation, which can be solved in some, over some domain with some boundary conditions, some initial conditions. Looks quite simple, right? But as I mentioned, you can't actually do that because of the restrictions put by wavelengths. Because to resolve the solution of Helmholtz equation, you need at least, very conservative estimate, 10 points per wavelength. But in fact, to do accurate simulation, you need a lot more. And that simply does not work. If you calculate typical wavelengths, multiply by the size of the domain, take it to the power of 3, no way it could work. No way. Although, typical question which a lot of people would ask, why don't just put in this equation into COMSOL? It can handle it very comfortably. No, it can't. Okay, so there are typical parameters. What we have some boundary conditions, soft-wall boundary condition at the surface, some radiation boundary condition somewhere far away, and we have some interfaces, which is very important for underwater acoustics. Interfaces, let's say, between the water and the bottom, where you have a jump of velocity, where you have jump of density, and which requires to take these interface conditions into account. Yeah? So how to deal with this equation? Well, the way we do is called, let's say, quasi-separation of variables. Well, you can't do real separation of variables. You can't use Fourier method directly because you don't have translational invariance in any direction. But you can do that approximately. That's a good thing. So you can introduce normal modes, which are, let's say, eigenfunctions of your vertical operator in this equation. And then these normal modes will satisfy normal usual orthogonality conditions. They basically represent something like eigenvibrations ducted between surface and the bottom. That's the typical way they look like. So there are a couple of the few normal modes in the typical shallow water environment. The most important of them are what we call waterborne modes, which are something close to discrete spectrum modes of this operator. These are modes which are localized in the water, exponentially decaying in the bottom. What happens if your bottom, you have some bottom relief variations? What happens if your depth of the sea changes? Of course, that happens all the time, right? Then the normal modes, they do adjust to the variations of depth. Likewise, they adjust to the variations of sound speed. Likewise, they adjust to any other variations of the environment, right? So you need to take these variations into account. So that's why I'm saying local normal modes. Local means this basis is different for different points of your domain. But they are super easy to compute, and we can compute them super efficiently. That's, let's say, very well-known result. And now, look, we have these normal modes, which are functions of depth, but which parametrically depend on x and y, which are horizontal coordinates. And we write this expansion over these normal modes, and we substitute that into our three-dimensional Helmholtz equation. This is kind of a similar to Galerkin type approximation, if you like it this way, although some people would say it's typical way to do model order reduction. Then what you have these equations for the coefficients in this expansion. And these coefficients vary. They are functions of only horizontal coordinates, so only x, y. And they take medial variations into account through these wave numbers of the modes, kj, which depend on x, y, which represent the variations of environment. And they take them into account through these mode coupling coefficients. So that's the general framework, how it works. Well, instead of one three-dimensional Helmholtz, you get several coupled two-dimensional Helmholtz, which is already a lot better, because instead of a lot of discretization points and depths, you can maybe 10, maybe 12, maybe 15, somewhere like that, tens, so to say, normal modes, instead of hundreds or thousands of points in depth. So that's already a big advantage. But for a while, we'll do even bigger simplification. We say, we drop the coupling terms. We do not allow normal modes to interact. We say, they propagate adiabatically. Why it's good to propagate adiabatically? Well, because you uncouple these equations. So it's a lot easier to solve numerically, of course, but why it's physically, let's say, justificable? Well, because the variations of bottom, if you go to a typical shallow water area, the slope of the bottom will be something around 1 degree, and that's a lot already. So in most cases, it's even less than 1 degree. So the variations of the bottom relief are really slow. And that's how it helps you to uncouple the equation and leverage this adiabaticity to uncouple the Helmholtz equations. And now you can solve them. But even that is not simple. Why? Because for a Helmholtz equation, two-dimensional in horizontal plane, what you need to set up is a boundary value problem with radiation boundary conditions, which are not super easy to take into account. Of course, you can truncate the domain and put some PML, some absorbing layers, whatever. You can do that, but it's still quite expensive. And the way we handle that, we do another approximation, which seems like we lose a lot, but in real situation, we actually don't. So the approximation is, we do as follows. We represent the operator in Helmholtz equation, like I omit the right-hand side, so it happens like away from the source, in the product of these two operators. And one of them corresponds to propagation forward, and the other corresponds to backward propagation. And if you are not interested in backward propagation, mostly interested in forward propagation, you are okay with retaining one of these terms, which brings you to this sort of equation with this operator square root. Operator square root of a differential operator. I'll discuss a little bit formal side of this thing later, but now let's operate with that on a formal way. So this is what we call pseudo-differential parabolic equation. So it's kind of sort of parabolic because it's order 1 in one variable, but it's sort of pseudo-differential because it contains pseudo-differential operator, which is operator square root. So this one is very well suitable for numerical integration. So what you can do, you can integrate it formally in a small step h in the evolutionary variable, which is x. And then you can obtain the solution at the step n plus 1 from the solution at the step n. Both of them are functions of just y. Through this, exponential of square root. Well, square root is a pseudo-differential operator. Exponential of square root is likewise a pseudo-differential operator. So it's not much worse. So this is the idea of the so-called split-step Padé method. Split-step Padé method consists in Padé approximation of this exponential of operator square root. So now we do this approximation by some Padé series of this form. And that brings us to the solution of several if you discretize in y, if you discretize in y in the transverse direction, if we do discretization, we end up with solving for every step of our numerical scheme, of our marching scheme, we end up with several sparse linear systems. And the number of linear systems for every step, number is p, is the order of Padé approximation. Usually you are okay with, let's say, order 5 or 7, in some extreme situation, maybe 11 or something like that, but no more than that. Yeah, so it's very efficient, very fast, and what's good about exponential square root, you can make a very large step in range, because you basically take out the principal oscillation out of your equation, and you don't need to resolve. And you can take the steps even larger than wavelengths, which is super surprising and super efficient. Yeah? And that allows to solve your equation efficiently. You need still to resolve some issues. You need to truncate the computational domain, for example, introducing some what is called perfectly matching layers. It's some absorbing layers on the sides of the domain. You can also introduce some transparent boundary conditions, which allow the waves to propagate out of the domain without reflection. So there are some issues. You need to be smart. You need to do some things, but it's more or less does the job. So a bit of a formal side about these things. So that's probably the only slide in my presentation where there will be some theorem. But I needed to include one, right, because of the place, right, because it's IMPA after all. So what about that? So does this square root even make sense? So what's the definition, how to define it formally, this operator? Well, it appears that it does. So you need to use stripe operator calculus, and if you have you introduce the notion of numerical range of the operator, which is this one, and the notion of numerical range is like all the set of all values, operator times function, scalar product with a function. Yeah. So if you introduce this numerical range, provided that your numerical range of your operator in the upper half plane of the complex plane, you can define the square root of the operator, and moreover, you can prove that this operator generates a contractive C0 semigroup, which is cool, which means that you have uniqueness, you have existence, and you have a well-positiveness of your solution, of your initial value problem for your pseudo-differential parabolic equation, and basically that makes this, let's say, brings mathematical justification to this measure. But, yeah. Now I'm going to show some examples. First, some more theoretical examples, how it works, like in some, let's say, idealized environments, and then I'll go to some practical examples, how this is actually used in practice. So this is, let's say, most traditional example you always have in underwater acoustics community. So whatever you propose as a tool to compute sound propagation in the ocean, you'll be asked to first to try your method using this coastal wedge. So you have a typical waveguide with sloping bottom representing something close to the beach, the part of the sea close to the beach, and and you need to compute the field in this domain. So the bottom is the surface is not penetrable because that's zero Dirichlet condition. The bottom is penetrable, so the acoustic waves can propagate in the bottom, and the task is to compute acoustic field. So this is what we do. This is typical, let's say, horizontal cross-section of acoustic field. So it's three-dimensional thing. But if we put, let's say, a horizontal plane in this domain through some fixed depths, so the field will look like that. Why it looks like that? What's wrong about, what's so specific about this pattern? Well, this pattern represents what is called horizontal refraction of waves. Refraction is a phenomenon which is responsible for appearance of mirages in the atmosphere and many other things. It means that wavefronts or rays get bended when they propagate through a homogeneous environment. In this case, horizontal refraction means that wavefronts get bended because sound tends to propagate to a deeper part of your area. So here I have my coast, and here I have deeper part, and this is like isobas, so the line of constant depth. And acoustic fields drifts towards larger depths, towards the area of large depths. So that's what you are supposed to see in this case. And there are some acoustic shadow, where you have no reception, you receive no signal because of this horizontal refraction. So there could be many reasons for horizontal refraction, but let's say typical classical picture, how it works, is this one. So what we do, we usually compute acoustic field along this line, and we compute acoustic field along some of these lines, horizontal lines. Lines parallel to y-axis. So this is xy plane. So look, this is the solution obtained along the x-axis. So that was quite a surprising result for many people across the community, because it shows that actually our adiabatic equations produce accurate solutions in this case, where everyone expected to be, let's say, mode coupling to come into play and strongly affect the field. Well, here, dashed line is a reference solution, which is obtained by something which is quasi-analytical. Red line is the solution of our mode parabolic equations, and there are blue circles. Blue circles represent the solution of mode parabolic equation with a step of 500 meters. And here, in this case, we have wavelengths of about 60 meters, which means we take steps in range 10 times larger than wavelengths, which is unimaginable for typical finite differences and finite element simulation because of the nice properties of this operator square root and in particular of its exponential. So it's super efficient because you can take such large steps. So that's and still you have an accurate solution. So for long range propagations, so this is like 25 kilometers, which is already somewhat long range. But sometimes people do hundreds and maybe even thousands kilometers. So it's not something like extreme. It's more like towards, let's say, small scale problems. That's what I want to say. Yeah, and later on I'll show the, let's say, the computational efficiency for this solution. Let me check how much time do I have. Okay, I still have some. Good. Okay, so now let me, okay, so there are some benchmarks showing that it also works for broadband, so for the pulses. For the pulses, you do propagation for every frequency, and then you do Fourier synthesis to compose the pulse. And it can't be done in any other way. So only in frequency domain, because of some reasons which I'm not going to discuss here, but you can also compute density flux, whatever. And now I'm going to discuss a little bit practical applications. So how this thing works in practice. So, well, one typical task we've been like all the time involved in Russia, like is simulation of seismic survey in the sense of noise mitigation. Because, of course, major part of energy of seismic survey goes downwards in order to, that you get some reflection, and then you know something about where oil and gas is, right? So that's how seismic survey works. So that's how it's set up in practice. So you have some seismic survey vessel which tows a huge array of receivers, right? So it can be several kilometers long. So it's an immersed thing. So it's and it emits some air gun signals into the water, and these air gun signals get reflected, and they produce, these reflections are recorded by this towed array, and then you basically solve the inverse problem. Yeah, so you know where oil and gas is, but that's not the point here. Yeah, the point is whenever you do that, you get some, let's say, undesirable sideward propagation of the thing, which is very loud because it's air guns. It's supposed to be very loud so that it reaches somewhere deep down in the sea bottom. And yeah, so it could affect marine animals. Yeah, so, and sometimes it actually does. And there are a lot of regulations in different countries, depending on the country, but now it's being homogenized somehow so that like people are trying to get to some common denominator, how much is allowed, how much is not, which it's slowly, but it's converging. Yeah, and so what's bad thing about this thing, about this task? Bad thing is that you don't know the source content. So you start finding out that in real life, you don't have knowledge about literally everything. You don't have knowledge about your bottom. Yeah, because when you are planning seismic survey, you still don't have this bottom information. You don't know what are the bottom layers. You can guess. Sometimes you do some educated guess. Sometimes you do some preliminary propagation experiments, but no more than that. So you have some estimates, but you don't know bottom. And what's even worse, you don't know the source. You know nothing, basically. You only have your equations, and you are left alone with this rude world of real life. So, and you need to somehow survive in that. So, but as I mentioned, there are always some measurements which do not allow to, which do not help to provide to get the full picture of what's going on. They can't provide you with a full soundscape, but which can serve as a reference for the model. So, if there is some let's say buoy which does the recording of this kind of signal somewhere close to the area where you actually do simulation, you can actually perform computations towards this buoy, compute the transfer function, how much at this specific frequency of the source is converted to this specific frequency at the receiver, and recalculate back and reproduce the spectral content of the source, and then use the spectral content of the source to propagate the field throughout the entire domain and compute your soundscape everywhere. That's how it works. Well, there are certain limitations, I would say. Just one of them, like this source, we can consider that as a point source, right? But it's like a huge battery of air guns. It's like several meters large, or maybe even tens meters large. Yeah, so it's a very big thing. But if you propagate for the distances of 5 or 10 kilometers, you can probably consider it as a point source, right? And what you actually restore, you don't restore the source content, because the source content is basically useless for you. You can know the signature of every individual air gun, and yet you know nothing. But through this thing, you can, let's say, somehow get the information of the thing as a whole. Thing as like this battery of air guns operating as a whole, and like some effective point source which it represents, it. Yeah. Then you can do computations, and yeah. So here we show how much is important to be really wide angle, to take many terms of this Pade series into account, and it appears that it's kind of really important because this is with many terms of Pade series. This is with just one. And you can see that there is a huge difference. Even if you integrate and you go for sound exposure level, so the integral quantity which contains all the frequency content of the signal, there is big difference. So you can't really take that into account with just one term of Pade series. So you need many of them. Yeah, so this is somehow represents the overall accuracy of the simulation. So look, here it is, the red thing is a signal, and the blue one is, let's say, our state-of-the-art tool. So they are kind of not so much similar as you would expect them to be, right? So there are a lot of discrepancies. But that's literally the best thing you can get, given the number of uncertainties you actually do have. And if you look at the waveforms, they look a lot different. But if you look at the sound exposure level, it's, let's say, I would say unimaginably accurate. So you can get this sound exposure level within like within the fraction of 1 decibel. Because it's, let's say, average of a large frequency band, and that helps you a lot. But looking at the waveform, no way you can get you can fully reproduce a waveform. At the very best, you can get something qualitatively similar. But that's how it is. And you don't need that. You know, you need sound exposure levels to estimate the impact. And sound exposure levels are actually quite good. This is an example, yet another example from this sort of activity, which was accomplished like in our project last year. So there is some area, there is some bottom relief, and the task was to produce the contours of this sound exposure levels, certain thresholds of sound exposure levels, and that's, let's say, final results more or less. So the contours, how far from the source it can still affect the animals. Yeah, so several contours which different sort of impact. Yeah, so green is probably try to avoid it to be too close to the area where whales actually live, and blue is okay. Something like that. Yeah, so this is some algorithmization which says how to somehow reconstruct the source from, let's say, reference measurements. Yeah, but there is also like an option for known spectrum, which actually never happens because we never know it. This kind of business. And next example I'm going to show is the example of shipping noise simulation. And this is like just to show how it might look. It's some pics from this international workshop showing like relative comparison of different models, right? So you have several curves which are kind of not exactly the same, but qualitatively, at least qualitatively similar, and most of the time quantitatively similar as well. So that's how people compare. They look at the signals of the waveform, and they look at the spectrum, and you see, while the signal is okay, the spectrum, sometimes it's okay, sometimes you have huge discrepancy. Yeah, so it's not something which is easily to solve. A lot of people are trying that, and there are still a lot of discrepancies in this matter. Yeah, so that's a problem which was solved for shipping noise modeling. So it's kind of, let's say, shipping noise monitoring station on the entrance to Vancouver Harbor. And it monitors the ships. And the goal is to estimate overall noise impact of the ship, of every ship passing by. And the goal is, finally, the goal is to find those the shipping companies who operate the ships which are too noisy. On one hand, the reason is clearly to get money, but on the other hand, it's kind of a, let's say, economical way to motivate people to operate, let's say, more quiet ships which do less impact to the environment. So when we started to solve this problem, you see, they didn't even expect us to be able to take into account, for example, bottom relief variations. So they told, why will you need bottom relief? You can't take it into account anyway because it's a three-dimensional problem. You can't solve that. We said, okay, we can take the bottom relief information from some international database. You see how coarse is that? So it's 4 by 4 kilometers area. So this is probably the shore, and this is like, you know, the step, and this discretization is very big. And we've shown that it actually does make certain impact on the sound exposure levels. And then they decided, okay, we can provide you with some measurements. We got some very realistic bathymetry, and we did computations taking into account this realistic bathymetry. And those are sound speed profiles, somehow they were from historical data, but the idea is that for this sort of monitoring, historical data should be utilized because you're not supposed to do measurement for every ship passing by, right? So, yeah, so that's a typical first order approximation. So first time you do simulation, you have this sort of result for the measurement, and here you have this sort of result for your simulation. Not even close. Yeah, but then you need to adjust your model. So now I'm going to briefly explain how it is adjusted. So what's on this plot? So see, here we have the distance from the measurement station. And here we have frequency bands. So we have our total frequency band separated in some smaller, which we call decadecade bands, or 1/3 octave bands, if it's, information makes sense for anyone. And the idea is to reproduce this, let's say, noise field produced by this ship passing by the monitoring station in all these decadecade frequency bands. Yeah, so the first try was super bad. Why it was super bad? Well, the answer is obvious, because you don't know a lot about the environment. Because they did provide us with some geological information about what the bottom is, but its accuracy is like terrible. You can't get anything reasonable from this like geological data. And what to do in this case? Well, the one thing you can do, you can try to adjust your model by acoustic measurement data. That's one thing, which is called geoacoustic inversion, by the way. I didn't include my results on this field into this presentation, but somehow the model can be adjusted. That's a good thing. Using sometimes even one ship passing by, you can adjust the model a lot. And we did adjust the model by just one point of ship trajectory, which is the closest one to the source. That's it. But again, yeah, so there is certain accuracy, small inaccuracy in the fact that we represent the ship as a point source. And in fact, everyone does. But some of the ships are quite large, right? So it's probably not so accurate. It's, let's say, first order approximation. Now we are working towards, with some of our colleagues, we're working towards including this real, more realistic model of a ship as a prolonged source with some directivity pattern, which is super important, actually. But let's say first order approximation. So that's the results of simulation. So the blue line is for the original bottom parameters, which we were provided from by these port authorities, which is like makes no sense at all. And when we adjust it, so the green line is measurement data at this closed point. And we adjusted parameters, not very much adjusted. We adjusted just two parameters of the sound speed, actually, in the bottom. We considered the bottom as a two-layer environment, one sediment and one basement, and we adjusted sound speed parameters. And then you get a lot better correspondence, right? It's still not perfect for higher frequency. So there are still things to fix. And one of the things to fix is, of course, the directivity of the source, which plays an important role in this high-frequency business. But for low frequency, where actually major part of the source energy is localized, is already quite good, right? So that's what we did, and we ended up with this one is the measurement, and this one is final simulation. It still looks different, but it's a lot more qualitatively and quantitatively similar. So that's the error which we ended up with, and this is the original one. So kind of a lot of purple in this picture suggests that it's a lot better, and it actually is. Yeah. And now, like, towards a bit more complicated model where we want to have this. I started with this adiabatic approximation, right? But we actually would prefer to take mode coupling into account, not to be adiabatic, right? That's what we would prefer. It's a lot more complicated, but it's not impossible. And I'll very briefly talk about that. Few more slides. Well, hopefully won't delay for a lot of time. So I get back to these coupled equations for mode amplitudes, which are coupled system of Helmholtz equations in 2 dimensions. And I rewrite it in the following form. So I take all these amplitudes, put them into a raw vector. Raw vector because I want coupling matrices to act on the right, while differential operator after discretization to act on the left. That's why I want them to be raws. And then when after discretization, this raw over functions transforms into a matrix representing these functions numerically. That's that's my goal. And now, what happens if you do that? Well, it's actually, you just need to rewrite your parabolic equation in this form, where these R, Q, and RS are right multiplication by some matrix. And instead of having this differential operator times some scalars, you have this differential operator times right multiplication of some matrix. That's it, the whole idea of it. And you can do the same exponential of a square root. And you can do just the same way Padet approximation. That was our idea. And then you can solve this problem with this operator x. But because you have matrix acting on the left and matrix acting on the right, instead of having matrix inversion problem, you have some sort of generalized Sylvester problem in this case, which is a bit worse, but not too much worse, and still doable. Yeah, so there is a bit of how this is performed, how this is formalized. And I want to show you a couple of pictures, like very final ones. So again, I go to this wedge, and I compute these solutions, these two. This one is computed within a adiabatic approximation. And this one computed with mode coupling taken into account. Not so much difference, right? So they are quite similar. But you can notice the difference here, here, and here. What are these lines? Well, they are actually cut off lines for the modes. So mode interaction happens at the places where you have, when one mode disappears and transforms into bottom mode. Mathematically speaking, that would be a discrete spectrum eigenfunction transforming into continuous spectrum eigenfunction because the waveguide is narrowing, something like that. Yeah, and in these very places, you have this mode interaction. But what happens if you take the difference? If you take the difference, you can see the full picture. It appears that this mode interaction occurs somewhere here, but then these waves generated by mode interaction at these points, they get also drifted by this horizontal refraction towards other points. But if you go sufficiently far away, so here it's like a smaller domain. So at the distance of 10 kilometers, you don't see that. At the distance of 5 kilometers, you like barely see that. But it could be relevant here near the source if you consider propagation towards the shallow depths. Then it becomes relevant. But it becomes a lot more intense computationally, so to say. Yeah, so here are some numbers, as I promised. Like I think it's my last slide or next to last slide. So this solvers, it can compute this thing in about 20 seconds. Like if it's C++ and about 5 minutes if it's MATLAB, something like that. Well, the closest competitor who can solve this problem and produce the same picture, this is like, let's say, some state-of-the-art 3D parabolic equation, which is similar but different because it operates in 3 dimensions. So it takes 23 hours to do this job for one frequency. Now imagine that you have not one frequency, instead you have tens of frequencies, right? And you want to simulate your pulse propagation and compute your SEL. Maybe 100 frequencies is okay for you, and 100 frequencies amount to 100 days. And this is for very low frequencies, so 25 hertz. So if you go for 100 hertz, then you will be, the computational time will grow cubically. If the problem will still fit in your memory. which it most likely won't. Yeah. So with coupled mode is a bit worse, but not too much. So that's my point. So it's still doable. It's still a lot more efficient than whatever competitor you have. Yeah. So there are still some challenges. The challenges is elastic bottom. The challenges is to make more efficient this adiabatic mode coupling thing. The challenge is to compute somewhat compute and simulate Stokes parameters. The challenge is to bring this geoacoustic inversion in, make it within the code so that it does not require any additional work by hand, something like that. But well, there is still work to be done. So that's it. And that concludes my presentation. Thank you very much for your attention.